In this video, we present Hover Widgets, localized interactive widgets for use in pen-based computing. Hover Widget icons are displayed after simple gestures are made by the pen, while positioned above the display surface. The icons can then be selected by bringing the pen in contact with the display. The Hover Widgets can have any sort of functionality associated with them. Here we are simply using them to change the color of our sketch. Hover Widgets do not require the use of supplementary barrel buttons or soft keys, which can be inconvenient or unavailable. They are implemented using the tracking zone of a pen input system. This is the area above a digitized surface which can track the location of the pen. In typical user interfaces, this state is used to display the current position of the cursor, as can be seen here. Hover Widgets utilize the pen information in this tracking state to look for specific gestures. Here we see a hover widget which can be activated by moving the pen right and then up. If this specific gesture is not made, the widget will stay hidden and cannot be activated. An advantage to using the hover state is that the gesture can be distinguished from ink. The gesture needed to activate a hover widget is defined by a tunnel. The tunnel is now being shown for demonstration purposes only. In a real application, the tunnel would not always be visible. If the cursor hits the walls of the tunnel, then the tunnel origin is reset to the current cursor position. This ensures that the hover widget will not be falsely activated. The tunnel is also reset if the pen touches the display. The one exception to these rules is if the first segment of the gesture is too long. In this case, the tunnel drags along with the cursor. This allows for scale-independent gestures. Similarly, if the second part of the stroke is too long, then the hover widget icon drags along with the cursor until a threshold point is reached. Once the cursor is above the hover widget icon, it can be selected, activating its functionality. Multiple hover widgets can coexist. Here we see 4 different hover widgets and their associated tunnels. Again, the tunnels are only being displayed for demonstration. It can be seen that each individual hover widget is updated independently, ensuring that it will be activated when its corresponding gesture is made. We have also explored hover widgets that have different activation gestures. Here we activate different hover widgets by quickly moving the pen in the shape of a spike in 4 different directions. Another example is a spiral-shaped gesture, seen here. Hover widgets can be effective tools for activating localized user interface elements. For example, instead of moving to the border of the display to select an item from a toolbar or menu, a hover widget can be used to display a marking menu. We have implemented a simple drawing application which uses hover widgets to access all of its functionality. A tool's marking menu is activated by moving right and then up. This can be thought of as a replacement to the standard bordering toolbar. An edit marking menu is activated by moving up and then to the left. This is a replacement for the standard edit menu. By moving down and to the left, the user activates a scrolling tool. The user can quickly switch between inking and scrolling without constantly moving back and forth between the bordering scroll bar. Lastly, the user can activate a right-click tool by moving down and to the right. This tool can be used to access functionality generally associated with the right mouse button of standard desktop applications, such as context-sensitive menus. Here a user is deleting ink strokes. We now show the system being used to create a simple drawing. We believe hover widgets are a promising technique for use with pen-based systems, promoting localized user interface interactions.